We're going to see that transformations is going to pop up in almost every chapter of this course. The only time we won't really use it is at the very end in the last unit. But otherwise, this transformations is going to come up throughout every other part of this course. And so because of that, it is a major part of your diploma exam that you will write in June. Okay, so a lot of it is memorization. You have to be able to look at a function and know what's going to happen to its base function. So we'll always be talking about a base function, what does it look like, and then what will it look like after all of the transformations. So we're going to be starting with a base function, y equals f at x. And that base function is going to be transformed by an equation. And so you need to memorize what each parameter does to a function. So you've got 4 letters that have been inserted into f at x. You've got an a, which is in front of the function. You've got a b, which is in front of the x. You've got an h that is hooked onto the x with a plus or a minus. And then you've also got that k at the end. Now you might see different letters used to represent these parameters. It's common, instead of h and k, you might see p and q. And in fact, in 20-1, when you worked on quadratics, I think it was x minus p all squared plus q. So sometimes different letters are used to represent these parameters, but that's not what is important. What's important is where it occurs. That tells you what that parameter does to the function. So you need to memorize this. You need to know this. What does each parameter do? So again, a is in front of the function. You're going to learn what that does to every graph. Same thing as b. It's in front of the x. You need to memorize what that does to the graph. Same thing with h, which is hooked onto the x with a plus or a minus. It's usually inside brackets, as well as the k value at the end. So in this first lesson, we're going to see the effects of h and k in y minus k equals f at x minus h on the graph of y equals f at x. So notice that I've written 2 different versions here. The only difference is that in the second version, the k is brought over to the y by subtracting it from both sides. And there's a reason why sometimes it's written like that, and we'll make that clear when we figure out what k actually does. So we're going to sketch these graphs for the given values of h and k, given the graph of y equals f at x, and then we'll also look at writing equations of functions after they've been transformed. So those are the things that we're going to be looking at in this first section. So on the next page, a transformation of a function alters the equation and any combination of location, shape, as well as orientation of the graph. So these are things that are going to change. The orientation, what that refers to is, you think about when you looked at quadratics in 20-1, the quadratics opened either up or down. That's what the orientation is. Okay, which way does it open? As well, we're going to see that the shape is going to change. The graph might get wider or narrower, okay? As well as the location. They're going to move around. They're going to shift left, right, up, down. So again, you're going to see which of these 4 parameters control these different transformations. Points on the original graph will correspond to points on the transformed or image graph. The relationship between these sets of points can be called a mapping. Mapping notation can be used to show a relationship between the coordinates of a set of points x, y, and the coordinates of the corresponding set of points x, y plus 3, for example. So that mapping notation is x comma y maps into, that's what that arrow means, x comma y plus 3. So on the diploma exam that students just wrote a week and a half ago, there was a question, a written response question on there where they had to talk about or explain a transformation. Okay. There was also a question in the multiple choice that dealt with a mapping notation. But the written response question was, they gave you a transformed function, an equation, and you had to explain a different aspect. And what it was is you had an original function f at x, and then you had a transformed function with a couple of the parameters that we've talked about here. And they were actually the a and the b parameters. A is in front of the function, and b is in front of the x. And so then they added those two parameters in there, and the student had to explain how you could determine the x and y intercepts for the new function from the original. That was the question on the diploma exam. Okay, so you're going to be tested on this, guaranteed, several times, because transformations is a major part of the course. So on the right, a transformation is a change made to a figure or a relation such that the figure or the graph of the relation is shifted or changed in shape. The mapping is relating one set of points to another set of points so that each point in the original set corresponds to exactly one point in the image set. One type of transformation is a translation. A translation can move the graph of a function up, down, left, or right. A translation occurs when the location of the graph changes, but not its shape or orientation. So this first example says the graph translations of the form y minus k equals f at x, which is the same as y equals f at x plus k. Right? If you add the k to both sides, that's what it'll look like. And we're going to see in most cases we will do this step if it's not already done for us. We will get the y letter by itself. So we're going to see what effect changing k has on a graph, as well as what effect changing h has on a graph. We'll start by graphing y equals x squared. We'll do y minus 2 equals x squared and y equals x minus 5 all squared on the same set of coordinate axes. So we'll do all three of those. We'll describe how the graphs compare to the graph of y equals x squared, and we'll also talk about what the mapping notation would look like. But in this case, we're starting with y equals x squared. So this is our base graph. We did y equals x squared in 20-1. It's a quadratic that opens upwards. And basically, I'm just doing a table of values in my head here. When x equals 0, 0 squared is still 0. When x equals 1, 1 squared is 1. When x equals 2, 2 squared is 4. Negative 1 squared is still 1. Negative 2 all squared is still positive 4. So this is what that graph looks like. And we always have arrows on the ends of our graph because the graph continues on in the same pattern. So there's the graph of y equals x squared. And as I said, I just kind of did a table of values in my head, but we can write it down for different values of x. What do we get for x squared? When x is negative 2 squared is positive 4. When x is negative 1 all squared is positive 1. 0 squared is 0, 1 squared is 1, 2 squared is 4. Okay, And so now we want to do y minus 2 equals x squared. Now remember I said we're always going to put them in the form y equals. So here you would add 2 to both sides and get y equals x squared plus 2. So for x squared plus 2, to get those numbers, we'll square the x like we just did, but now we will add 2 to those values. So all the values here will be 2 more than they were for y equals x squared. 2 more than 4 is 6. 2 more than 1 is 3. 2 more than 0. 2 more than 1. 2 more than 4. So for y equals x squared plus 2, this gives us our new points. Our negative 2 comma 6. Negative 1 comma 3. 0 comma 2. 1 comma 3 and 2 comma 6. So this is the graph of y equals x squared plus 2. Whereas the original one was just y equals x squared. The shape of the graph didn't change. It didn't get any wider or narrower. The orientation didn't change. Both graphs open upwards. What's changed is its location. All the y values were 2 more than the y values from the previous graph. The effect then is that the graph shifted up 2 units. That's what happened here. The graph shifted up 2 units. So this plus 2 at the end of the equation, that is a k value. Yeah? All the y values were 2 more than they were previously. And the net effect is that the graph shifted up 2 units. And in this case here, our k value is positive 2. So k is at the end of the function. The difference between h and k is this. H is hooked directly onto the x with a plus or a minus. Normally the x minus h is in brackets. This value of 2 is outside the bracket. It's not hooked directly onto the x. Instead, it's hooked onto the x squared. That's the difference between h and k. H is hooked directly onto the x with a plus or a minus. If there is an h value, the x minus h will be in brackets. Whatever happens to the x will happen to the x minus h. In this case, the x is squared. If there's an h value, the x minus h will be all squared, which is what the next equation is. When we graph x minus 5 all squared, that will be an h value because it's hooked directly onto the x with a plus or a minus. Whatever happens to the x happens to the x minus h. In this case, the x is squared, so the x minus h is all squared. This is the reason that this 2 is a k value of plus 2. And the graph shifted up 2 units. Okay? Now, for the third graph, which is x minus 5 all squared, this would be an h value of positive 5. In order to make x minus h look like x minus 5, you have to replace the h with the positive 5. Okay? The general equation is x minus h. Same thing on the previous page, I guess on the first page. Notice the x and the h are hooked together by a minus. It's x minus h. That is the general form. When h is positive, the equation stays x minus. If h is negative, though, the equation will become x plus. The value of h is always the opposite of what it appears to be because of that. So for this graph that we're going to do next, the value of h is positive 5. So for x minus 5 all squared, You're going to take your value of x, you're going to subtract 5, and you're going to square it. So when x is -2, you'll take away 5. That'll give you -7. Squared is 49, which we don't have room for on our graph. But we'll find some points that we do have room for. When x is -1, -1 take away 5 is -6. Squared is 36. Again, we don't have room for those on our graph. But we'll find some that do. 0 take away 5 is -5. Squared is 25. 1 take away 5 is -4. Squared is 16. 2 take away 5 is -3. Squared is 9. So I need to get some more points here. When x is 3, 3 take away 5 is -2. Squared is 4. When x is 4, 4 take away 5 is -1. Squared is 1. When x is 5, 5 take away 5 is 0. Squared is 0. 6 take away 1 is 1. Squared is 1. 7 take away 1 is 2. Squared is 4. So these points I'll put on this graph. The point 3, 1, 3, 4. The point 4, 1, 5, 0, 6, 1, and 7, 4. So this is the graph of x minus 5 all squared. Let me fix this. So 4, 1, or 3, 4, I should say. 4, 1, 3, 4. There we go. Something like that. So in this case here, the value of h was +5, and the graph shifted over 5 units to the right. The shape of it didn't change. It didn't get any wider or narrower. The orientation didn't change. It's still going up. What's changed is its position. It shifted 5 units to the right. And in this case here, the value of h is +5. So, excuse me, when we describe how these graphs compare to the graph of y equals x squared, so we can write that below here. From y equals x squared to y minus 2 equals x squared, which is the same as y equals x squared plus 2, the resulting transformation is that the graph shifted up 2 units. We're describing our transformation, that's what happened. The graph shifted up 2 units. And our mapping notation is that x, y mapped into x, y plus 2. Because the graph shifted up 2 units, that means that you added 2 onto all the y values. That's what we did when we did our table of values. We added 2 onto all the y values from y equals x squared. And then for y equals x minus 5 all squared, what happened here, and maybe I'll write this in brackets, or Here the value of h is positive 5, and the result is that the graph shifted 5 units to the right. You can always also use the word translated. Translated 5 units to the right. But there's two components that you need. You need the number of units as well as the direction. Here the value of h was positive 5, and that shifts the graph 5 units to the right. Our mapping notation, when that happened, we added 5 onto all the x values. And the mapping notation needs both parts of this. You need the x comma y, you must have the arrow, which means it maps into, as well as the second part. Okay, so there's the mapping notation. Again, in this one above, this was a k value. Our k value was positive 2. And it shifted the graph up 2 units. And this is the reason why sometimes it's written with that 2 over beside the y, because it is changing the y values. It's going up by 2. We added 2 to all the y values. This is the reason why sometimes it's written with the k value over on the left with the y variable. All right. So for the your turn, it says, how do the graphs of y plus 1 equals x squared as well as y equals x plus 3 all squared compared to the graph of y equals x squared? And then we'll also write our mapping notation. So for the first one, if we go from y equals x squared to y plus 1 equals x squared, or y equals x squared minus 1, we get x squared or y by itself here. We have to subtract 1 from both sides. This is a k value of negative 1. So this will shift the graph down 1 unit. K value of negative 1 means the graph will shift down 1 unit. And so our mapping notation would be x comma y maps into x comma y minus 1. If it shifts down 1 unit, you're subtracting 1 from all the previous y values. And then from y equals x squared to y equals x plus 3 all squared, this is an h value. You see the difference between the two equations. For a k value, it's not hooked directly onto the x, it's hooked directly onto the x squared. For an h value, it's hooked directly onto the x. It's inside the brackets. Whatever happens to the x, which in this case the x was squared, also happens to the x minus h. It's all squared. That's how we know that that 3 value represents an h, and it's actually a negative 3 because the value of h is always the opposite of what it appears to be. You're always comparing it to x minus h. What value do I have to put in for h so that I'll get x plus 3 inside the brackets? Well, if you have x minus h and you want it to become x plus 3, the only way that works is if h is negative 3. And then the minus minus will become a plus positive. And so because h is negative 3, the graph is going to shift 3 units left. And the mapping notation would be x comma y maps into, if it goes 3 units left, that means you're subtracting 3 from all the x values. So there's our mapping notation. X comma y maps into x minus 3 comma y. Okay? So again, you need to memorize this. You need to be able to look at an equation, pick out what parameter is being changed or added, and then remember what effect that'll have on the graph. You're going to be tested on this several times. So on the next page, it kind of puts it together. Sketch the graph of y equals, now that's the absolute value of x minus 4 plus 3. So our base graph would be y equals the absolute value of x. Our base graph would be y equals the absolute value of x. So what does that look like? Well, our graphing calculator will show us what it looks like. If we go to y equals, now to get the absolute value function, if you go to math, over to number, and the very first choice in that list is absolute value, ABS. So you go to math key is on the left, third row down. Scroll over to the second column, which is number, and the very first choice is ABS for absolute value. Now, on this calculator, it actually has absolute value symbols that will put the X in and then hit enter. Older operating system, it goes ABS with an open bracket. So you put the X in there, close the bracket. That's the absolute value of X. Zoom 6 to set my windows to their standard settings between -10 and +10 on both axes. An absolute value graph is just a big V. The absolute value of -1 is 1. So that is the point -1, comma 1. The absolute value of -2 is 2. The absolute value of -3 is 3. The absolute value of -4 is 4. So it goes through -4, comma 4, -3, comma 3, 0, comma 0, 1, comma 1, 2, comma 2, 3, comma 3, 4, comma 4, and so on. Again, essentially, it is a big V. That's what it looks like. And now we're going to transform that graph using y equals the absolute value of x minus 4 plus 3. In this case, h would be +4. Remember, h is hooked on to the x with a plus or a minus. Whatever happens to the x minus h. In this case, the x is inside the absolute value symbols, so the x minus h would be inside the absolute value symbols. And the value of h is always the opposite of what it appears to be. H is +4. So this graph will shift 4 units right. As well, though, we have a k value. K is outside the brackets. In this case, when we say brackets, it's the same as the absolute value symbol. K is outside the absolute value symbol. Our k value is +3. So this graph will also shift 3 units up. All points will go 4 to the right and 3 up. So I'm going to start at this point, -4, comma 4. It's going to go 4 to the right and 3 up. Take me up there somewhere. -3, comma 3 will go 4 to the right and 3 up. -1, comma 1. 4 to the right and 3 up. 0, comma 0. 4 to the right and 3 up. 1, comma 1. 4 to the right and 3 up. 2, comma 2. 4 to the right and 3 up. 3, comma 3. 4 to the right and 3 up. So there's our new graph. And our mapping notation, we went 4 to the right, so we added 4 onto the x values. we went 3 up, so we added 3 to the y values. So again, you need to memorize this. You need to be able to look at a function with these parameters in there and know what it does to the base graph. You're going to be tested on this several times throughout the course. So for this next one, this is a transformation of y equals x squared. It's y equals x plus 5 all squared, take away 2. Our base graph is y equals x squared. That goes through 0, 0, 1, 1, 2, 4, negative 1, 1, negative 2, 4. Okay. We always have arrows on the ends of our graphs because that pattern continues forever. And we've got 2 parameters here. We have an h value of negative 5. We just hook directly onto the x with a plus or a minus. X minus h is in brackets. Whatever happens to the x happens to the x minus h. In this case, the x is squared, so the x minus h will be squared as well. And the value of h is the opposite of what it appears to be. H is negative 5, which means the graph is going to shift 5 units left. As well, we have a k value of minus 2, which means the graph is also going to shift 2 down. So all the points will go 5 to the left and 2 down. 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 So here's our new points. Our new graph. Our mapping notation. It went 5 to the left, so you're subtracting 5 from the x values. 2 down means you're subtracting 2 from all the y values. Okay? So these next examples, we're given our base graph and a transformed graph from that base, and we want to write the equation. In the case of question A, you're given the actual equation for the base graph. It's f of x is x squared. But notice for the second one, for question B, there is no equation to give us that graph, so it's just y equals f of x. That's our base equation. But for the first one, our base equation is f of x equals x squared. And note, it says determine the equation of the translated function in the form y minus k equals f of x minus h. So this tells us that it's only h and k that are going to be changed, because those are the 2 parameters that were given. So you need to just look and see what change did the graph go through. And we'll just take the vertex. The vertex went from 0, 0 to negative 4, negative 5. Right, we went from the point 0, 0 to negative 4, negative 5, which means the graph shifted to the left 4 units So the value of h would be -4 because that's what h does. As well, it shifts down 5 units, which means k is -5. So our equation, I'm going to write it in the form that we normally write it in. If h is -4, and maybe I'll write it here. First, in terms of h and k, the general form is x minus h, in this case all squared, plus k. If you plug a -4 in for h, the minus minus will become plus positive. So it'll become x plus 4 all squared minus 5. There's our equation. And the form that it asked us to write it above had the k value over with the y, so we would add 5 to both sides, and that's what the equation would look like. Our mapping notation, because it went 4 to the left, we subtracted 4 from all the x values, and because it went 5 down, we subtract 5 from all the y values. So there's the mapping notation. So for the second one, we're going from f at x to g at x, and note that the points are labeled A and A prime. B became B prime, C became C prime, and so on. So we're just going to choose one of these points. If I go from A, which is the point -5, 2, to A prime, which is the point -1, -7, the graph would have to shift 4 units right, as well as 9 units down. You guys can get down and get your textbooks, because everyone know what their student ID number is. We need that. If you don't know what your student ID number is, I can get it for you. You just got to let me know. Okay, down to the library, get your textbook. Where are you in this list? It's alphabetical by last name. T?
Alphabet.
Cedric? 39754. 39754. Your name?
Chase.
Last name?
Packard.
Paquin? 14710. Okay? All right, so we said that the graph would go 4 to the right as well. It will go 9 units down because it goes 4 to our right. To the right, our h value is 4. 9 down tells us that k value is -9. So g at x, that is our transformed graph, is a transformation of f at x. So when you add h and k into f at x, that's where this expression here comes from. The h is hooked directly onto the x with a plus or a minus. It's inside brackets. The k is outside the brackets. And so our h value is positive 4. So when you have x minus h and you replace the h with 4, it becomes x minus 4 inside the brackets. And then the 9 is at the end, the minus 9. K is outside the brackets. So our mapping notation here, as we went 4 to the right, we're actually adding 4 to the x values. 9 down means we're subtracting 9 from the y values. So the term image point, that describes the point that is the result of the transformation of a point on the original graph. So the image point is the new point after the transformation has taken place. Okay, and this will all be posted on Google Classroom. There'll be a copy of the notes on there as well as the video, so you'll be able to refer back to that later today. Once I add you all, I'll put this on there. Okay? So for these next ones, it says describe the translation that's been applied to the graph of f at x to obtain g at x, and then determine the equation of the translated function in that form. So again, the fact that it's only h and k, those are the only two parameters we're working with right now. In the case of question A, g at x is a transformation of f at x, and f at x is defined as the absolute value of x. So g will be in terms of an absolute value function. We're going from f to g. So we'll use the starting point of the graph, and there's actually a special name for that. It's called the cusp, C-U-S-P. You'll be tested on that. You will not be tested on that, but that is the starting point of an absolute value function. In the case of a quadratic, that's called a vertex. In the case of an absolute value, the word is cusp, C-U-S-P. But that's the point that we're going to compare. To go from the cusp of f to the cusp of g, the graph will go 4 units to the right and 6 units up. So it's going to shift 4 to the right, which means h is 4, and also 6 up. So k is 6. So g will be written in terms of f. The original function is an absolute value function with an h value of positive 4. So if we're going to put our h and k values into that equation, this is what it'll look like. And so now if we actually insert them in there, our value of h is positive 4, so it'll stay x minus 4. And our value of k is also positive 6. Our mapping notation, because we went 4 to the right, you're adding 4 onto the x values as well as adding 6 onto the y values. The difference from question A to B, though, is that in question B, there is no equation that we can write to give us that graph. So it's just going from f at x to g at x. You're going from A to A prime, or from C to C prime, or D to T prime, it doesn't matter. If I go from C to C prime, C is at the point 6, 2. C prime is the point -2, 5. So this graph would shift to the left and up. It's going to shift 8 units left, which means our h value is -8. And it'll shift 3 units up, which means our k value is +3. So g at x is a transformation of f at x, and if we put our h and k parameters in there, remember, h is hooked directly onto the x with a plus or a minus. Whatever happens to the x happens to the x minus h. In this case, it's in brackets after the f. The k is outside the brackets. And when you put a negative value in for h, the minus becomes a plus positive. So it's become x plus 8. and our k value is positive 3. Nope, because the base graph is just f at x. If the original graph was a y equals x squared, then the new one would have the brackets squared. But that's not what we're starting with. We're just starting with f at x. And our mapping notation, it went 8 to the left, so you're subtracting 8 from the x values, 3 up, so you're adding 3 to the y values. Right? So these next examples, write the mapping notation from y equals f at x for each of the following. So for the first one, our h value will be positive 3, our k value would be negative 2. An h value of positive 3 means it's going to go 3 to the right. In other words, you're adding 3 to the x values. K is negative 2, so you're going to go 2 down, or you're going to subtract 2 from the y values. For question B, our h value is negative 1, because the value of h is always the opposite of what it appears to be. K value is positive 5. So in this case, the graph is going to go 1 to the left, or you're going to subtract 1 from the x values, add 5 to the y values. Question B, or C, excuse me, I would probably get y by itself. In this case, there is no h value, or we could say h is 0. Our k value is positive 8. So the mapping notation here, the x value doesn't change. Only the y values are increased by 8. So x maps directly onto x. In question D, again, I would get the y by itself. Our h value is negative 4. Our k value is also negative. And there's our new points. Okay? This next one, given each function in the form y equals f at x, insert h and k into the appropriate spot. So remember, whatever happens to the x happens to the x minus h. In this case, it's multiplied by 2. K is outside of that. X minus h is in brackets. Whatever happens to the x happens to the x minus h. In this case, it has a coefficient of 2. For question 2, the x is squared, which means the x minus h would have to be squared. K is outside the bracket. For question 3, the x is in the denominator, so the x minus h will be in the denominator. K is outside of that. For question 4, the x is under the radical, so the x minus h will be under the radical. The radical acts just like brackets. The k is outside of that. Number 5. X is inside the absolute value, so the x minus h will be inside the absolute value. K is outside of that. And for question 6, the x is cubed, so the x minus h will be cubed. K is outside of that. So write each mapping notation used to describe the transformation from y equals f at x to the following functions. For number 1, h is inside the brackets, hooked directly onto the x. It's always the opposite of what it appears to be. H should be 3, k would be negative 1. So if h is positive 3, that means the graph goes 3 to the right, or you're going to add 3 to the x values. K is negative 1, which means the graph's going to go down 1, or you're going to subtract 1 from the y values. For number 2, the x minus h is inside the brackets. In this case, the radical acts just like brackets. H is hooked directly onto the x with a plus or a minus, and the value of h is always the opposite of what it appears to be. Our h value here is negative 4, which means the graph is going to shift 4 to the left, or you're going to subtract 4 from the x values. K is positive 2, you're going to go up 2, or add 2 to the y values. Number 3, this is just a transformation of the line y equals x. This is what this represents. A transformation of the line y equals x. That's our base graph. The value of h is the opposite of what it appears to be. H is negative 5, which means the graph is going to shift 5 to the left, or you're going to subtract 5 from the x values and add 7 to the y values. Number 4, whatever happens to the x happens to the x minus h. In this case, it's under 1. And the value of h is the opposite of what it appears to be. So h would be positive 9, k would be positive 5. For question 5, whatever happens to the x happens to the x minus h, in this case inside the absolute value symbol. And the value of h is always the opposite of what it appears to be. In this case, they're both negative 3. Which means you're going to go 3 to the left. You're going to subtract 3 from the x values and subtract 3 from the y values. And for number 6, whatever happens to the x happens to the x minus h, in this case squared. Value of h is the opposite of what it appears to be. So that'll be a positive 1. K is negative 8. If h is positive 1, you're going to go to the right one. You're going to add 1 to all the x values and subtract 8 from the y values. The word determine is important. On a diploma exam or on a unit exam or a quiz, when you see the word determine, that means you got to show your work. What steps did you follow in order to get your solution? And in many cases, it'll say determine algebraically. So again, you need to show the steps you did algebraically in order to get your solution. So in this case here, we want to determine the vertical translation that would be applied to that equation so that the translated image passes through the point 2, comma 2. Well, if there's a vertical translation, vertical means up and down. That means the k value is going to be affected. We're going to have a k parameter added into this equation, and k goes on the end. It'll be hooked directly onto that 4. Because we're told it's a vertical translation, that means it's going to go up or down, which means our k parameter is going to be introduced. And if the graph passes through the point 2, comma 2, it means that that point must satisfy the equation. When x equals 2, y would have to equal 2 as well. So I let x equal 2 and I let y equal 2, and now I just have one variable left. I have a variable k, which I can solve for. 2 take away 3 is negative 1, squared is positive 1. So 1 plus 4 is 5 on the right. And when you subtract 5 from both sides, k is going to equal negative 3. So the vertical translation that would need to be applied is that the graph would have to shift down 3 units. That is the answer. And for the next one, it's a horizontal translation. So that's an h value. Whatever happens to the x happens to the x minus h, which in this case is under the radical. And in this case, it must pass through the point 17, comma 8. That backwards. I let x equal 17 and y equal 8. I now need to solve for h. And I would do that by first squaring both sides, which give me 64 on the left, and on the right side the square and square root will cancel each other out. When I subtract 17 from both sides, I'll get 47 on the left. And that's what negative h is, so positive h would be negative 47, which means the graph would have to shift 47 units left. That is the answer. That is the vertical translation that would need to happen so that translated graph passes through the point 17, comma 8. Yeah. If h is negative, it goes to the left. In the equation, if we were going to write the equation, it would be y equals the square root of x plus 47. That's where the positive would be. But when h is negative, the graph goes to the left. In the equation, it'll be written as x plus 47, though, because the value of h is always the opposite of what it appears to be. Okay. On the next page, there's a summary of what we've learned, the key ideas. And then on the following, skip a page, then there's an assignment there for you to work on. It is out of the textbook, but I put it in here in your package. I will post these solutions to Google Classroom. So as soon as I'm done here, I'll add you all to Google Classroom. You'll receive the invite, and then I'll post a copy of the notes. I'll post the video. I'll also post the key to this assignment. There will be some assignments I will ask you to hand in, and I'll mark them, and those will not be posted, those solutions, but most of them will not be for marks, and the solutions will be posted. I can't stress how important it is that you do the practice. To me, math is no different than music or sport. You got to practice to get good at it. This is a hard course. I firmly believe that this diploma exam will be the hardest diploma exam you write. You got to know your stuff. You have to. And there's a lot of stuff you're going to learn, and the way to stay on top of it is to do your practice daily. You do that, and you'll have a much easier time on all of the assessments, including the diploma exam. There's a lot of stuff you have to know in this course. Okay? So do the practice. That's how you're going to remember things and get good at it. And I'll get these answers posted as well. So, okay?